Good morning, students. In this video, I will continue the linear momentum and I will do more application on the linear momentum of a particle and Newton's second law. And also I will explain the linear momentum of a system of particles and try to find the relation between the linear momentum of a system of particles and that of its center of mass. Okay, let's start. So here in this example, we have a ball of mass 50 kg hits a wall with a horizontal velocity. Speed is 20 meters per second as shown in the figure. The time, here 30 meters per second, but the ball rebounds back with the velocity v2. And the time of contact between the ball and the wall is 20 milliseconds. The question is determine the average force exerted by the wall on the ball. It means here when the ball is in contact with the wall, you know, when they are in contact, the wall exerts a force on the ball. Of course, at the same time, the ball exerts a force on the wall. So this is the force exerted by the wall on the ball while they were in contact. Because there is a force here and there is a change in the velocity, the first thing must flash in our mind is Newton's second law. Okay? So Newton's second law means that sum of forces, as we studied in video 1, sum of forces acting on the ball is equal ma, right? But I prefer to write it in terms of momentum, since momentum is proportional directly to the velocity. So dp over dt, you can also write it p prime, the derivative, right? This is derivative. This means that while the wall is in contact here with the, while the ball is contact with the ball, there is the weight, right? And the normal, which is this force, the normal exerted by the wall, which is F wall on B. So F exerted by the wall, in reality, this is the normal force on the ball plus the weight of the ball is equal dp over dt. But he said neglect the weight of the ball, means this is approximately 0. Why? Because in this situation the weight is very small compared to the force of the wall on the ball. Okay? And also we want what? The average. Remember the average? In the average we do not know the detail of motion. That's why we use delta t. Okay? So this is the average force exerted by the wall on the ball. Okay? And because this is average, as I told you in chapter 1, over delta t, right? So dt becomes delta t, and here we want the change of linear momentum, which is delta p. Remember the meaning of average? It's like the average velocity, delta r over delta t. Always when we say average, we mean delta t, okay? Good. So this will imply that, but delta p, what does delta p mean? It means P final minus P initial. The final linear momentum, which is P2, minus the initial linear momentum, which is P1. And delta t, which is the time interval, is given here, time interval delta t. Okay. Now, this is a vector equation, and I cannot replace numbers or vectors by number. First, I have to eliminate the vector notation. How do I do this? I have to choose a frame of reference or reference axis. Let's choose x prime x as the reference axis. Let me use the green color. So here, x prime x. You can choose x prime x in the sense of force, but I will take it in the usual sense you choose in mathematics. This is the sense of x prime x, okay? This is x prime x. Now, let's replace in this equation. Here, minus f average, right? This is a unit vector I. Why minus? Because this force is opposite to the positive sense of x prime x, equal delta p. Delta p is p final minus p initial, means minus m v final or v2 I. Why minus? Because look at the sense of velocity here and look at x prime x, they are opposite, right? So minus. Minus here. Here there is minus. So minus pi, which is m1 v1. m1 v1 I. Notice here, this is v1, has the same sense as x prime x, okay? Over delta t. So let's do the calculation. Let me insert a new page here. If you do the calculation, then you get the following. F average, you eliminate the minus sign and the unit vector. F average is m into v2 plus v1. Notice here, all of these are positive number. Be careful. And if you replace, you get the answer 125 Newton. This is very big force. Now try to compare it with weight. The mass is 50 gram, means 0.05 kilogram, and W equal mg is 0.5 Newton. Notice 0.5 Newton is very small compared to this, okay? This is an important application on how to apply Newton's second law during collision, okay, with an object. Now we have another exercise which is very nice. I will keep it for you as a homework and you solve it with your teacher in the class. Okay, we have a football player kicking the ball like this. The ball hits the ground at this point, which is 15 meters away. The question is, determine the impulsive force F exerted by the player's foot on the ball, and the time of contact is 100 milliseconds. Try to do this, I think, difficult but nice exercise. Now, the linear momentum of a system of particles. You know the meaning of system of particles, means the group of particles, okay? So by definition, for one particle, we observe that the linear momentum is P equal mv. For a system of particles, it is what? P of the system is P1, linear momentum for the first particle, plus P2 for the second particle, plus for the last particle. Okay? And don't forget, this is a vector equation, not scalar. You mean you cannot replace numbers directly here instead of these factors. So let's recall the meaning of the center of mass. The position from last year, the position vector of the center of mass of a system of n particles is this rule. Remember the barycenter theorem in mathematics. M1, R1. R1 is the position vector of the first particle. R2 is the position vector of the second particle, etc. So in this rule, you can calculate the center of mass. Or you can divide it like this. Xg, let me put it, leave a space. Here it is. Implies, or you can write it equivalent in this way. X abscissa y, because position vector r is xi plus yj. So m1 x1 for the first particle plus m2 x2 plus, then you count all the particles. mn xn over the total mass, m total. Similarly for the y, equal m1 y1 plus m2 y2, then you count all the particles, mn yn over the total mass. Clear? I think this is simpler. Any problem? Good. Now we want to verify an important theorem. Theorem of the center of mass. This theorem states that the linear momentum of a system of particles equals the linear momentum of the center of mass. Means we want to verify this. P of the system of particles is equal P linear momentum of the center of mass, G. So here m is the total mass of the system. Then you can write this. Where it comes from this relation. Okay? Now let's do the derivative. What's the derivative of the position vector? It is a velocity vector, right? So you get this rule. mv equal m1 v1, etc. Because the derivative of r is v. Derivative of r1, v1, etc. But what is this? This is p1. What is this? This is p2. What is this? This is pn. So all of this represent what? Linear momentum of the system of particles. But what is this? Total mass. What is Vg? The velocity of the center of mass. So conclusion. Hence, Pg equal P of the system of particles. Let me put it here. We get now the important rule. The linear momentum of the center of mass equals the linear momentum of the system of particles. Okay? So, in the next video, we continue the application on the conservation of linear momentum. See you next video. Good. Take care. Bye-bye.